So essentially, when we want to solve problems involving electromagnetic radiation and waves, we follow the same procedure in factor labeling problem solving as we have with all factor label problem solving and conversions. We start by reading the problem carefully and writing down all the information we're given with numbers and units. But in this case, we don't need labels because everything in the problem is referring to this electromagnetic wave. Consequently, it's unnecessary to label everything as wave, 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 and wave. It's redundant. So we're just going to use numbers and units in this simple problem. And we're given a frequency of 2.0 times 10 to the 20th hertz. But we don't write hertz because hertz is a derived unit that takes the place of the actual units inverse seconds. And it's going to be much easier to see what to do if we write the seconds instead of the hertz. Now, because it's an electromagnetic wave, we immediately have two other pieces of information that we can use. One is that all EM waves have the same speed, the speed of light, which is 3.0 times 10 to the 8th meters per second. Not only that, but if the problem involves energy, we have another constant that's true of the photons of all electromagnetic waves, namely their energy-time relationship, known as Planck's constant, to three significant digits. Planck's constant is 6.33 times 10 to the negative 34th joule seconds. And so even though these last two values are not given to me in the question, as soon as I see that I'm dealing with an electromagnetic wave, I know that I have these, and they're a critical part of my data that I can help solve the problem with. Then, to start the problem, I ask what quantity is being requested. And this says, what is the wave length? That's a length. So I go into my data and spot the answer. Time, time, energy, time. This is the only length I see. So I start with the answer. 3.0 times 10 to the 8th meters per second. That essentially is my answer. However, I've introduced a quantity I don't want in my answer called time. Well, the only thing that cancels a time is a time. And I have a time here in the denominator of the frequency and a time here in Planck's constant. Now, if I use this time in Planck's constant to cancel the time, I'm going to introduce units of energy, joules. And I don't see joules anywhere else with which to cancel them. But if I use this unit of time, seconds, I'm not introducing a new quantity. All I'm doing is adding a number to the equation. So I'm going to cancel my time units with these time units. However, since they exist in the denominator of a frequency, I would want to divide by or invert and multiply by this amount. Namely, for every second, you have 2.0 times 10 to the 20th waves. And the seconds cancel, and lo and behold, the only units left are units of length. However, step 5 in my method is you then always make sure the units are consistent with what was requested. And we wanted micrometers, we have meters, so we have one more step to convert those meters to micrometers. And 1 micrometer is 10 to the negative 6 meters. Cancellation of meters, we get our answer in the units we want, micrometers. Grab our calculators, multiply 3.0 times 10 to the 8th, and we divide by 2.0 times 10 to the 20th, we divide by the 10 to the negative 6, and with two significant digits based upon the fact we've rounded the speed of light off to 2 digits, and our frequency was given with 2 digits, we get 1.5 times 10 to the negative 6 micrometers as an answer. Moving right along, again, we have a problem. What is the energy of a photon of blue light if the blue light has a wavelength of 455 nanometers? I write down everything that I know with numbers and units. The labels are redundant because everything would be labeled waves. We've got a wave, we have a wavelength, so we just leave the wave part off for expediency. But because it's electromagnetic, there are two numbers I'm given that are not stated explicitly in the problem. The speed of all electromagnetic radiation and the energy relationship of all photons of electromagnetic radiation. And then I ask, what quantity is this problem asking me for? And it's asking me for energy. And if I've done the first step right, energy somewhere, and the only place I see units of energy are in Planck's constant. So I'll start the problem with the right answer, energy. It's hard to go wrong when you start with the right answer. But of course, my right answer usually comes along with a quantity I don't want in my answer. And in this case, the quantity I don't want is time. Now, this is a length, so the only other place I see time is in the speed of light. So if I simply multiply by the speed of light, my time units cancel. However, I did introduce length units. So they need to go too, because I just want energy. I don't want energy length, I just want energy. So I'm going to have to cancel this length. The only thing that cancels a length is a length. And I do have one, but the units are inconsistent. Nanometers can't cancel meters. So a quick conversion from meters to nanometers, and I'm on my way. 1 nano means 10 to the negative 9th of something. Meters cancel and are replaced by nanometers. And those can be canceled by the nanometer wavelength given in the problem. If I put it in the denominator, it cancels, and voila, all we have left are energy units. We multiply 6.63 times 10 to the negative 34th by 3.0 times 10 to the 8th. We divide by 10 to the negative 9th. We divide by 455 nanometers. And with a 2-digit number based upon the speed of light being rounded off to 2 digits, we get a value of 4.4 times 10 to the negative 19th joules as our answer. Well, a problem worded slightly differently, but approached exactly the same way. We have a photon, so we have an electromagnetic wave, and both of these quantities are in play yet again, 3.0 times 10 to the 8th meters per second, and 6.63 times 10 to the negative 34th joules seconds are both quantities I can use in this problem. And another value I'm given in the problem itself is 3.0 times 10 to the negative 18th joules of energy. So I've got everything clearly labeled with their units. And then I read the question, and it says that a photon has a certain energy, and we're asked, what is the frequency? And I know that frequency is represented by inverse time units. Now, I'm going to start with time, but I see time units both in the speed of light as well as in Planck's constant. So I need to make a choice. Which should give me my units of time with which to start the problem? And I think that if I start with these units of time, I'm going to have to cancel energy. And clearly I have an energy value to cancel that energy value. But were I to use these units of time to start the problem, I'd introduce a length. And I have no other length to cancel that length, so I'd hit a dead end. So clearly, if I want inverse units of time, I'm going to take this value, the entire value, and invert it. 1 over 6.63 times 10 to the negative 34th joules. Seconds, excuse me, joule seconds. And I now have my inverse units of time. Of course, the quantity I need to cancel in this case is energy. And I have energy, so I can cancel the energy with the quantity of energy given, leaving me inverse time units, otherwise known as a frequency. I grab my calculator and simply divide 3.0 times 10 to the negative 18th by 6.63 times 10 to the negative 34th. And based once again on this 2-digit rounded off speed of light, I want a 2-digit number, and that number is 4.5 times 10 to the 15th. And now that it's an answer, I don't write it as inverse seconds. I write the derived unit for inverse seconds, hertz, to express my frequency. And I've completed the problem yet again. And as another example, if I have another electromagnetic wave, I once again have two quantities I immediately know. 3.0 times 10 to the 8th meters per second, and 6.63 times 10 to the negative 34th joule seconds. In this problem, I am also given a value of energy, 4.0 times 10 to the negative 18th joules. Once again, once everything's clearly numbered and labeled, I ask what quantity the problem wants. And in this case, it wants a length of the wave, a wavelength. I immediately scan through my data, and the only place I see length is right there in the speed of light. So I have to start with the answer. And I essentially have my length. Well, I've introduced a quantity I don't want, and that quantity is time. I have to cancel time. And the only thing that cancels time is time. And the only other place beside the speed of light I see time is Planck's constant. So I must use Planck's constant in order to cancel the time units. And they do. However, that does introduce a new quantity, which is units of energy. But I can cancel energy units because I was given energy units. And if I simply divide by 4.0 times 10 to the negative 18th joules, all quantities cancel except for the wavelength. Of course, I always check to see if they wanted specific units of wavelength, and they do not, so I'm ready to calculate my answer. So I grab the calculator and I multiply 3.0 times 10 to the 8th meters per second by 6.63 times 10 to the negative 34th, and I divide by 4.0 times 10 to the negative 18th. And I get the two-digit answer of 5.0 times 10 to the negative 8th, and my units, of course, are meters. Completed yet again. As a final example, once again, we have a radio wave, an E&M wave, so we have the same available data, 3.0 times 10 to the 8th meters per second, the speed of all electromagnetic waves, 6.63 times 10 to the negative 34th joules seconds, the energy relationship of all electromagnetic waves, Planck's constant, and in this particular problem we're given a length of 2.0 kilometers. Again, I read carefully, and it's requesting the energy of this wave. And the only units of energy in all my data are included in Planck's constant, so I know immediately how to start. I start with Planck's constant, negative 34th joule seconds. There's my answer. All that remains to be done is cancel quantities I don't want. In this case, I do not wish units of time, and the only units of time in my data to cancel them with are in the speed of light. So I would multiply by the speed of light, and the units of time cancel. That leaves me with units of length, and fortunately I was given a length in the problem. The only problem here is that the units are not consistent with each other. Kilometers can't cancel meters, so I make a quick conversion. Meters, kilometers, 1 kilo of anything is 10 to the third of that thing. I cancel, and now I can cancel this length in kilometers with the given length in kilometers. Kilometers cancel. I grab my calculator and enter 6.63 times 10 to the negative 34th times 3.0 times 10 to the 8th, divide it by 10 to the third, and divide by 2. And I get a tiny, tiny value expressed in 2 digits because of these two measured numbers. And when rounded correctly, it comes out to 9.9 times 10 to the negative 29th joules, an absolutely tiny amount of energy. But then again, radio waves are the longest of all electromagnetic waves, and being the longest, they have the least energy. They're the least energetic waves. So consequently, I would expect a very small energy for each photon of such a wave. And this is how we complete electromagnetic wave problems using the factor label method.